Jess.
Montana.
And John.
And this is Experiment 5, Recycling Aluminum.
The purpose of this experiment is to prepare a sample of potassium alum from aluminum and determine the percent yield. A few definitions you might need to know are the limiting reagent, which is the reactant that has the smallest stoichiometric amount in a reactant mixture and consequently limits the amount of product in a chemical reaction. And vice versa, the excess reagent is what is left after the limiting reagent is completely consumed. And for this experiment, we consider aluminum to be the limiting reagent and all other reagents to be an excess reagent. The stoichiometric coefficient is the number written in front of ions and molecules in a chemical reaction to balance the number of each element on both the reactant and the product side of the chemical equation. For example, on the reactant side there are 2 aluminums, and on the product side there are 2 aluminums. The materials for this experiment is the aluminum scrap for the reaction, scissors to cut the aluminum, a 250 milliliter beaker to put your solution, and KOH and H2SO4 for the solution, a 50-50 mix of alcohol and water to rinse your product, and a filter flask and a Buchner funnel for filtration.
The procedure was broken down into 4 basic steps. 1, we dissolved our aluminum with a strong base. 2, we prepared a solution of soluble aluminum sulfate. 3, we synthesized the alum. And 4, we isolated our alum. For number 1, to dissolve our aluminum, we started with 0.50 grams of aluminum scrap cut into 1 to 2 millimeter strips, and then we added 25 milliliters of 1.5 molar KOH solution, which you can see here. Next step was to prepare a solution of soluble aluminum sulfate. So we took this beaker prepared in step 1 and we heated it over here for about 30 minutes. And as it heated, it released excess H2 gas, which you can also see in the product of the balanced chemical equation. And in order to maintain our volume, we had to add distilled water as necessary. Next, we collected the filtrate by filtration, and then we had to use more deionized water as needed. So what we did is we took what was in the beaker and we put it into our funnel and filter paper, and we used a glass stirring rod, and we filtered out our water, and we left the extra scrap pieces in the filter, but we got our filtrate using filtration. And after we got our filtrate, we cooled the solution to the room temperature, and then we used an ice bath to cool it even more. Next, we synthesized the alum. So we added 9 molar H2SO4 or hydrogen sulfate until the pH was around 1 to 2, as you can see demonstrated here. And we had to keep adding the hydrogen sulfate until it reached this. And part of our observations was that a white precipitate formed. For number 4, to isolate our alum, we had to collect the crystals by vacuum filtration using a Buchner funnel and filter flask, which you can see here. So we had to put our crystals in on top of the filter paper in the Buchner funnel, and we attached a hose which created the vacuum suction through our water faucet. And as it suctioned out the water, we were left with just the crystals. And in order to just have the hydrated crystals, we had to wash it with 10 milliliters of cold methanol. And then in order to just have our crystals without any water left on them, we had to transfer the crystals onto a watch glass and let them dry overnight. And after all that was over, we weighed what crystals we had left. Now on to our results of the experiment. To find the moles of aluminum that we started out with, we have to take our 0.5 grams of aluminum, divide by the molar mass of aluminum, and that gives us 0.019 moles of aluminum. Now, in order to find the moles, moles are covered in the aluminum product. The moles of aluminum are covered in the aluminum product. We have to keep in mind that the atomic mass of our hydrate is 474.384 grams, and our atomic mass of our aluminum, 26.982 grams. So the next step we do is we find the percent comp of the aluminum in our hydrate. So we take the atomic mass of our aluminum divided by the atomic mass of our hydrate, and that gives us 5.6878%. Now, the next step in finding the moles of Al in the aluminum product, or the hydrate, is we take 1.52 grams, which is the mass of the crystals at the end of our experiment. We multiply the crystals of the aluminum product by the percent comp of aluminum, and we get 0.08645 grams of aluminum in our alum product. In John's experiment, he started with 3.23 grams of the hydrate, so when he multiplied by his percent comp, he got 0.18372 grams of aluminum. Now the last step is to convert from our moles of aluminum from the grams of aluminum to our moles of aluminum. And to do that, we take the grams that we have divided by the atomic mass of the aluminum, which gave us 0.003, and it gave John 0.006 moles of aluminum in the aluminum product.
Next we shall talk about the theoretical yield. And the theoretical yield is the amount of product produced assuming that the limiting reactant is used up completely. To find the theoretical yield of this equation, we need to know our limiting reactant, which is the 0.5 grams of aluminum. We then use a stoichiometric relationship to get to the grams of our hydrate. And to do that, we go from grams of aluminum to moles of aluminum to moles of our hydrate to grams of the hydrate. And to get our numbers for this, we need to know the molar ratio, which comes from the balanced chemical equation.
To find the percent yield, you take the amount of dry alum collected and divide it by the theoretical yield of the alum. For mine and Jessica's experiment, we got 1.52 grams of hydrate over 8.8 grams of the theoretical yield, which gave us a 17% yield. And in John's experiment, he took 3.2 grams of his alum and divided it by the 8.8 theoretical yield, which gave him a 37% yield. And in this instance, he has a higher percent yield because he has fewer errors in the experiment than mine and Jessica's.
In conclusion, the theoretical yield of the hydrate was the same for both groups, but our varying experimental errors resulted in different percent yields. Some of the possible errors that might have accounted for this was the spill of alum crystals after vacuum filtration when transferring, which is what happened to Jessica's group. And as you can see by the diagram, they lost quite a few of their crystals down the sink. Other errors might be improper measurements when weighing, or being impatient and not waiting for the scales to fully level out. If the volume was not maintained at the 2/3 requested by the procedure during the heating of the 1.5 KOH solution and the aluminum. Yet another error, and the last we have displayed, is if solid particles made it through the filter paper during filtration due to a small tear on the paper.